Okay, so now we're gonna talk about this video segment of like about 4 lectures is going to be based on two properties known as the extreme value property and the intermediate value property. Okay, so let's first talk about the extreme value property. This, as we can see by the name, it basically, the extreme value property talks about the limit, talks about this is not the limit of a function that we're talking about. This is actually the limit of a domain, the range of a domain, the minimum and the maximum value that are contained in the particular domain of a function. So there has to be a formal way of expressing that. So let's just do that. I'm going to write down the formal definition first and then try to explain to you guys what that means. So for that, we have to establish a set, right? It's a set of real numbers. So this particular set of real numbers that we just made up on our own has to have a maximum m only if m, the maximum element, belongs to this set, right? And for all other values belonging to this set S, x is less than or equal to n. So think about this for a second. Initially, when I read this, when I was doing Calculus 1, I didn't pretty much get it, but it's saying something very basic and something that's so primitive that we don't even need a definition for it. But we're gonna express it using this definition, which is this is probably going to make our life a lot easier when we're doing examples. So S is a set of real numbers. It could be any set. It could contain 1, 2, 3, 4, right? Let's just assume that as an example initially. What the extreme value property is suggesting is that this set S that's constructed of real numbers has a maximum m only if m, the element, belongs to this set, right? And for all particular values of x for that set, x is less than or equal to m, or basically m is greater than all the values that are contained over here. So over here we know that the maximum is 4, right? What it's saying is initially the first condition is that m belongs to the set. 4 belongs to the set S, right? We just made S up and we know that 4 belongs to S, right? You just do. It makes sense. It's right over there. That's the first condition. And the second condition is that 4 is greater than all other values that are present in the set S. That's basically the extreme value property. So if you think about it, it's something very basic, right? But expressing something like this in a general form such as this by constructing a set to which all this can be applied to is very important, because when we're doing examples, we're going to realize how open and closed intervals are important to this and are related to this in so many different ways, right? So I just need to revise a little what an open interval is and what a closed interval is. You could refer to the earlier videos on this. Basically, for a closed interval, if I'm talking about the set, this set would include A as well as B. So these closed brackets are going to include B and A, right? But if they're round and they're not square brackets, then A and B are not included. So for something like 4, 5 and 1 bracket, this suggests that the set would contain 4, but it would not contain 5. It would contain values up to 4.99999, but it would not contain 5. That's something important you guys need to know before we move on to examples. Okay, so another important thing that you guys need to know as well is that this isn't entirely the extreme value property. So this just tells us what a maximum is. We're going to apply this to functions for the extreme value property to be applicable, right? So we've talked about the max, right? We know that an example would be something like the set S equaling 1 and 2, right? So the maximum m according to this is 2. The first condition is that m belongs to S, right? 2 belongs to S, and that it's greater than all other elements. Since 2 is greater than 1, it's the maximum of this set. Another example, talking about this set. That's basically the real set. You know that the real set it can go up to as many elements as it can, right? And that it contains it contains lots of different numbers, but it does not contain infinity, because infinity is not a number, it's a concept. It's a very, very large number that keeps on getting larger. So what I'm saying is this real set does not have a minimum or a maximum element, right? because it can be anything we want it to be. It can be as large or as small as possible. So for this example, the set S, which is defined to be minus infinity to infinity, open interval, has no maximum, right? Let's try to find a minimum property. So what we just studied was the maximum property. The minimum property, well, it's very similar to the property we just talked about. It talks about a set S. Now it's the same set, it's a set of real numbers, you know that, right? And the set S would have a minimum if M, which is the minimum in this case, belongs to the set S, and the other condition, for all other values of x belonging to S, x is greater than or equal to M. So this is the opposite of this inequality over here. So in that case, M had to be greater than all other elements. In this case, M has to be less than or equal to all other elements for it to be considered to be a minimum, right? So if I have an example over here, let's talk about S. 1, 2. We have the minimum M equals 1, right? Because it belongs to the set and it's less than or equal to every other element in the set. So it has a minimum. But what about the real set? Well, the same argument would apply. It would neither have a minimum nor a maximum according to the argument we just discussed over here. Now we're going to talk about the extreme value property. Since we've defined what a minimum and a maximum is, it's going to be very simple for us to now consider this property that talks about that. So the extreme value property suggests that if you have a function f that is continuous at every point where in a closed interval a comma b. So basically a would be included and so would b. So if x is varying from a to b, it would lie in this particular range, right? So what I'm saying is, for a function f which is continuous at every point in this closed interval that lies from a to b, if this holds true, then f attains a maximum value m that we talked about in the previous section, as well as a minimum value, which is small m, at least once in the interval. Again, if you think about it, this is something very fundamental. It's like saying in an interval from 1 to 5, 1 is going to be the minimum and 5 is going to be the maximum, and they're going to happen exactly once. But what you guys need to understand is we had to write it up in a very formal way so we can use it. In mathematics, everything has to be described in a very precise manner. So this is why we've chosen this definition. As a recap, we know that if a function f is continuous at every point in the closed interval a to b, such as 1 and 5 over here, then f it has to attain a maximum and a minimum at least once in the interval. It could attain it multiple times, but what's more important is that the function at least has to attain it once. One for each, like one minimum and one maximum. So in the next video, we're going to do a few examples so that we can use this property that we just learned.